Right. Welcome to IEEE Blockchain Get 2022. This is what we call the Q5 session, starting at 6 p.m. Pacific. We run up through 7:30 p.m. for the next 90 minutes. So this is going to be a very fascinating session. My name is Gora Dada. I'm the moderator. I also happen to be the chair for this entire conference. And it is definitely my privilege to have two excellent speakers coming up. Sanjay Chatterjee will be the first speaker, and Jim St. Clair would be the second speaker. And for this particular block, as you all have seen, this session, we are going to talk about digital twin, digital engineering, all kinds of fascinating emerging areas. This conference, as we short name is GET, which is Global Emerging Technology, Blockchain and Beyond. So blockchain being one of the emerging technology, but there are other aspects of emerging technologies we are also covering during the 5 days of our activity. And with that, I will go ahead and request Sanjay Chatterjee to give an introduction of who he is and take on presentation from there on. And Sanjay, let me make you the co-host.
Yeah. Thank you, Gora, and good morning and good evening.
Just a second. Okay, before you proceed, let me just. Yeah, continue, Anna, because I have to get you be the co-host. So continue talking.
Yeah. Thank you, Gora. Good morning and good evening to all of you. So today's topic, as you have seen, I will be talking about metaverse of engineering and approach to digital twin. But before I start my presentation, for the last couple of years, I was going through this digital twin, metaverse, and all those technologies associated with this and all. And I found a lot of different perspective of looking this to, or rather, the digital twins area. And every perspective has got their own merits and demerits. And so I, being a technology guy, of course, an entrepreneur in background, I look into a entrepreneurial background. But maybe a quick introduction, Gora, I don't know whether they all have it about me or maybe...
No, please, absolutely. Everybody's new here. So.
Yeah, I did my engineering and master's in mechanical engineering. And then I joined one of the leading automobile company in India for 4 years. Then I was one of the youngest developer in a startup company called Castor Systems in Silicon Valley for around 8.5 years. So that was acquired. The product was acquired by IBM in 2011. Meanwhile, I left and I started Ideation Technology Solutions, Ideal Analytics Solutions, and InTheory Solutions, these three companies. Ideal Analytics was a company based in the data science. That was our core area. So we work in data analytics, data engineering, and of course, anything related to data. So that's how we had these three companies. We mainly run it from India, the headquarters being in Kolkata in India, and we have offices in France and some presence in US as well. So most of our customers are in US and Europe. And few of the areas that we work with is with World Bank Group, which is in a lot of verticals like in transportation and healthcare. In UNICEF also, we have worked in healthcare a lot in the countries like Iraq and all. So a versatile experience, a small team of product experience background. That is what I have and my team has. So with this, I will, I also chair the NASSCOM East here in India. NASSCOM is the body for the software and mainly the software export companies in India. So I chair the eastern region of NASSCOM as well. So with this introduction, I will start with today's topic, which is metaverse of engineering and approach to digital twin. So my definition of digital twin, the way I look at it, is it's a 5-dimension thing. So of course, the first dimension is time. The next is the 3 other dimensions are latitude, longitude, and altitude, which is the location. And the last or the 5th dimension is basically your problem or issue. So if you see, the digital twin has been incorporated or now is being popular, and it is being implemented in the areas right from tourism to rocket science everywhere. And I was surprised the growth that it has happened for last 1-2 years and maybe recent times in the undersea area. a huge, a kind of implementation has started happening there. So today's speech will be primarily focusing on the engineering side of it, like industry, where this metaverse of engineering, where the digital twin fits in there. So I'll share my screen. Please let me know whether you can see my screen. Do you see my
Yes.
presentation?
Yes. Perfect.
Okay, great. So okay, so this is where the metaverse of engineering, the way we have already done it for a couple of industries like oil and gas, power, energy, utility, manufacturing, and these sectors. In fact, oil and gas being the primary one, they have started entering into this arena maybe 5-6 years before. There was another area in parallel which was coming up, which is there in the industry for maybe last more than few decades, which is BIM, building information modeling. But what I'm talking about it today is basically a BIM for engineering, maybe, or digital twin for engineering, a bit different than the architectural BIM thing, but it is basically more of an engineering. Like, even if you can say, like, you can build a digital twin model of a thermal process, that is also possible. So digital twin is basically a set of, the way we want to make the clone of it from an architectural perspective, from a civil perspective, from a mechanical perspective, electrical, lighting, everything. So that way we don't limit ourselves, and it has got some steps the way we had experienced while we implemented a couple of solutions for our customers. So I will primarily go through our, this presentation based on whatever the steps and processes that we have come across while implementing digital twin for the engineering companies, and that will reflect in my presentation. So if you see in the engineering field, there are two broad kind of projects. One is the greenfield or brownfield engineering, which is where it might be related to civil structure or anything, and second one is the reverse engineering. Honestly, the reverse engineering of digital twin part is a bit more here. The reason is many of the plants and big industries, they are already existing. So they need to upgrade themselves to digital transformation. And for them, reverse engineering through digital twin also is kind of, probably at this point of time, I would say it is 60 is in the reverse engineering digital twin and 40% comes from the greenfield engineering. With this broad category, the greenfield is a pretty straightforward. We are building something, we have a planned layout, we have got every bit structural, civil, architectural, machineries, everything. So we are planning, we have all the drawings, we have got all the specifications, we have got every modeling that is required to be done. We can build those models, we can have a progress monitored, and of course, right from the commissioning to erection to implementation, every stage we can have a small process. What makes us interesting, what is like where we are really trying this for a reverse engineering as well as greenfield cases for industries like oil and gas, power, process, infra, etc. So if you see, honestly, we have different kinds of industry. Broad category wise, there are discrete manufacturing, process manufacturing, there are infra, there are power and utility, of course, oil and gas. So this kind of industry, it comes, and of course in manufacturing also there are lots of variations, like there are even with the IIoT stuffs and all. So this process has become so complex. There are CKD, there are a lot of so with a diversified industry in the background, the first challenge that comes in our mind is the asset that has to be monitored, that has to be measured, that has to be tracked. Any asset, be it, when I say an asset, it might be a machine, it might be a structure, it might be a small sensor which is giving some data, it might be anything, any equipment that's existing in that physical world. So then the moment we have identified the asset for that particular industry, the first thing that comes in our mind is how to create the physical replica, the digital replica of the asset. This is the first step. And there are multiple ways of doing it. For forward engineering, it is easy. For greenfield project, it is easy because you have got the drawings and all from the architectural, and then you can build it. For a reverse engineering cases, this is more interesting, and there are technology like the first one, as you see, like LiDAR-based, which is a laser technology thing. So big static, so you can just put those small LiDAR cameras, and you can have a complete 3D point cloud generation, which is not easy, but which is not difficult too. Also, in a very complex, soft floor or maybe any industry, like imagine an oil and gas has got kilometers wide in a long piping. So there we cannot have LiDARs, fixed LiDARs. So there we can have a drone based, which is the next picture that you see here. So the LiDAR can have we can have a drone based imagery. And from that, we can reconstruct the model. The idea is when we are creating this 3D model, which is the actual replica of the physical model, either we do it by this reverse engineering, we do it by LiDAR based or very high resolution imagery. From there, we can generate point cloud. From the point cloud, we can generate the mesh. From the mesh, we can generate surfacing. From the surface, we can generate each and every component of the item. Again, when I say component of the asset, it might be as small as asset like what you see here, or it might be a small valve, or it might be a complete big machinery or a building or a bridge or anything. So this is the first step. The moment we do this, a 3D model is generated with each and every bill of material is generated, and you can generate the drawing or whatever. This is, and the data from the point cloud. It helps you to even build this in a super speed way. There are even tools these days available. This will help you to reduce your manual effort, and it auto generates these objects. Accuracy is not 100% yet, but still with 70-80% accuracy, you can do this reverse engineering, and rest 20% you have to do manual work. But imagine an existing plant which is running for 10 years, 15 years, whatever, and you are really do not have maybe all the drawings even, but still you can reconstruct and make a complete 3D model of the whole plant. After creation, the next step comes is the connect, which is where we are now entering deep into the digital twin part. This is where the data being captured, the creation, and then connecting the data from different sources. Broadly, the sources for this data is static as well as dynamic and real-time in nature. Of course, static data we have got about the specification of the item, etc. We have got process data, which is in real time. It comes from the PLS, PLC, and SCADA. And PLM, ERP data, IT systems data, that also comes in. And most importantly, the data which is coming from different sensors, MES and all, which is IIoT, industrial IoT or IoT sensors. Now, these broad 4 categories of data, external and internal, these are mainly internal data sources. And not only that, we can connect the data with the external data sources as well, because at some areas, like for example, somebody is constructing a bridge in an area which has got some maybe steel, small, kind of where the weather might have an effect. So you can really fetch the information from the external sources, which may fit into the model. Later on, I'll show you in my subsequent slides. But the data, internal as well as external data sources, the idea is once this data is captured, we need to superimpose this data on the model. That is the third step. So we have done the first step, which is created the 3D model. We connected the data, and the next step after the data is connected, how we intellify it. The first step of intellification, or intelligizing, the way we call it, is tagging the data, both static as well as dynamic, on top of your model. This is the very, very first step. If you compare it with any GIS system, so it's basically GIS for engineering. I mean, normal Google map, if you can imagine, there are different layers of information. And similarly, you can imagine your 3D model where you can walk through VR or through augmented reality, you can see that. Now, this particular 3D model, you can imagine as a base map, and different information of different kinds as different layers. So the first thing is you can do a tagging of the equipment or any asset. The advantage is enormous. The moment you tag it, this can be available anytime, anywhere. I will show you how the next you do the interaction between this model and all. The next is the simulation and prediction part, be it risk management, be it an anomaly detection. Like the picture, if you see in the left here, this is a small picture. I don't know whether it is visible, but if you see the red item shows like, there is some risk or some issue in that particular item. And this kind of visual representation helps the operations huge. Like the moment you see something is wrong, you get an alarm, and then the visualize your problems even before they are occurring, much before they are occurring. So be it risk prediction, be it anomaly, even be it predictive maintenance. So this is really something matters. I can give you a small use case in between that will explain you on how this kind of small intervention. We did a project for one of the power plant. They had a milling machine in power plant. So the milling machine, as you probably know who are from the engineering background, it basically crushes the coal, make it in a smaller shape so that can be fed into the furnace. Very simple. So in the bottom, there is a roller, and the top, there is also a roller. So this rotates. Maybe the bottom one is static and the top one rotates only. And in between, there are balls. It's like a bearing, ball bearing. So in between these two plates, circular plates, there are balls, steel balls. And this size of the ball is 3 feet, 3 to 4 feet, like this big. Now, the interesting part is during over time, and there are generally 11 or 12 balls, in this. And these rollers, they get worn out over time. And the cost of replacement is huge, in millions of dollars for a set of this thing. So what they do, if they have got a timely maintenance, they have to replace all the rollers for all the milling machines. It's like a huge cost. But if this can be identified and a simulation they can see, like, this milling machine, the balls has to be replaced in 6 months time, maybe 1 month before we get an alarm, and visually, so that they can be replaced. And it is always better to have a predictive maintenance instead of a timely maintenance. So these are the small areas, even within the engineering in different departments, different sections, this kind of predictive things can be incorporated. The corrosion in the pipe, if it is in oil and gas, and even in utility also, is like a huge problem. Sometimes the pipes are insulated, and inside that, measuring the corrosion becomes a very, very complex. There are direct ways and there are indirect ways. Like you can have an indirect way of measuring the flow, pressure, etc. from the sensors. And then we can have a kind of, I would say, a correlation with if there are more corrosion, the space between will reduce, and it will affect the flow of the fluid or the gas. So accordingly, from that, indirectly, we can identify and you can give an alarm beforehand. So these kind of, there are thousands of use cases. Honestly, we have done quite few already, and I think it's never ending. I mean, it's like a huge, and every industry has got this kind of interesting use cases. And of course, the last part is like, once you have the data, once you have superimposed the data, you can literally do any kind of analytics and AI/ML for predictive models and all. Like the example, the last example I will give about thermal power plant. This modeling of the thermal process itself can be done. The next step after we intellify. So now you had created your model, you have connected the data, you have intellified that. Then what? Then the next thing comes, how you interact with the whole ecosystem. This interaction is very, very interesting, and it has got its purpose. Every interaction mode has got its very nice purpose. The first interaction you'll be requiring is like asset monitoring. This is any companies, any industry. This is the probably for the big industry, that is one of the challenge. So as asset monitoring and visualization is one. This is very standard. So you'll have got a 3D asset management, and also because the whole model is there, every part is identified and tagged. All the data that you can see, you can walk through a plant and see and go in front of, stand in front of a machine, see the pressure gauge, see the pressure reading, like that. So it's basically as if you are going physically, seeing that whatever. If there are some anomaly of some kind of an alarm, you can see. You can see it using your VR glass. You can walk through the plant and you can identify the place very easily, and you can send the operations guy accordingly. So there are two ways of interacting. One is through VR. This is primarily being used from the control room. And one of the major use case for VR here in this digital twin is from a training perspective mostly. And the AR is from a support and operation perspective, the service perspective. The AR, it is very, very simple, yet very effective. Every machinery, we can just put a small QR code, just still QR code, and the person working in the plant just puts his camera to the QR code. Immediately that particular part pops up along with all the tagged information, and you are done. He can do every interactions from there. He doesn't have to remember the specification of the part. He doesn't have to bring any paper. He can examine the part. He can write whatever he wants. So every process can be made easy for the operations guy. There are very interesting problems even through virtual reality. In big plant, the major problem is even the identifying the sensors. In a small power plant, more or less on an average, there are 200,000 to 300,000 sensors. It's like a very standard, very small power plant, I'm saying. Very, very small. So these 300,000 sensors, whenever one sensor or a couple of sensors gets damaged, to identify the location takes maximum time, thus cost. So through VR or through AR, the beauty is the moment you go to that particular pipe, say there is something happened and some sensors have to be replaced. You know which sensor is giving the alarm, you know its location. So immediately you don't have to spend time. So you know exactly location, because this is not a small 6 inches pipe. This is maybe, a 5 meter diameter is like a big area. So you don't know, and the sensor size is in millimeters or centimeter. This helps. So these are the real life small problems, but the interaction becomes through virtual walkthrough and through augmented reality. Of course, the asset management part, which is regular use with the 3D visualization capabilities, this is there. So the next is the act. This is probably you need a much matured organization to really act. We can stop even to the interact level, that gives enough ROI. But if you want to really go towards a fully automated system, then this is one of the most important thing probably. So this triggers the actuators. Now, after you interact, you find the anomaly, you get those alarms and notification. Some action has to be triggered, be it a hydraulic, be it electrical, be it a mechanical, thermal, anything. Now that actuate or the action will trigger some actuators, which will trigger some change of machine, or which will do some, which will activate some sensors to do something. Now this is where the loop completes. Now, if you see, connecting this all 5 steps, the physical world has assets. We are putting different a 3D model of that. After that, we are putting different sensors and getting some data. We are connecting all the data, both internal and external. After the data is connected, we are doing a lot of prediction, simulation, and actionable insights we are getting, as well as we are doing intellification, which is information tagging, both static and dynamic. Then we are interacting with VR and AR and doing the asset management. And then we are actuating so that the real world anomalies, whatever is being found, can be rectified in a loop. Now, this is the whole ecosystem that we have found. I don't have to, in fact, talk about, the benefits. I know you probably are aware, but just to asset monitoring, maintenance, cost minimization, remote planning, in, like this kind of industries, the why I was having this question, like, which are the industries, and we had an internal debate, like the way the digital twin is coming up, why this is, has been, some of the industries, they are very, very ahead of the others. Honestly, I mean, oil and gas being far ahead of many of the industries, other industries, honestly. And then it came the power utility, then, manufacturing. Interestingly, the reason for the adoption of this kind of technology is primarily, as I think, the cost of failure being very high. So in these industries, and the digital twin really helps to minimize the cost of failure. And of course, with a huge improvement in the operational aspect of it, this really helps excellent time management for service and everything. Couple of industries I think you all know, but what we have come across is oil and gas. As I mentioned, I will not talk elaborately about these industries. Later, if you want to, I'll be happy to have one-to-one discussions later on. You can connect me, but just to give you a quite brief about these are the industries I've seen. This digital twin is being used enormously, and like in oil and gas and refineries, there are huge pipelines. So piping structure is one of the very, very important. Any leakage will be disaster. So those kind of environment, this is important. The advanced plant management is APM softwares. Then the power is another. The cost of failure is huge, very, very similar. And in power, there are different departments where, as I mentioned, the milling and also everywhere it is useful. And most of these are, the existing engineering plant. Generally, a power plant has got a life of 20 years. Depends upon the size and all, of course. So imagine, like, a 10 years old power plant, which has another 10 years life. This kind of technology intervention probably increase the lifespan of the plant in another maybe 20% or 25%. That is also an upside of this. Infrastructure, I didn't mention much about it, but just give you an example, like, what we are doing it even in Kolkata. We got a project from World Bank, very interesting. So see, this is a very classic use case of where the digital twin can be used in any area, honestly, because transportation is one of our vertical that we work in. Kolkata, where I live, which is a eastern part of India, which has got a river going through it. This is very, very congested. And we had this river 700 kilometers upstream of the river. So we were analyzing, like, the freight flow of the river and the passenger flow. Freight flow is currently 3%. Can we increase it to 30%? This will improve the GDP. That was the basic problem statement. And how can we do a freight flow analysis and passenger analysis for all the approach roads across this river? So there are different points where you have ferries, going to and fro and across. So this traffic simulation, so what we are doing now, 1 kilometer in each side of the river, we're taking 3 millimeter to 8 millimeter high resolution drone imagery. From there, we're building the model, and then we are superimposing the transportation data on top of that, and then we are making a simulation model so that with this higher impact, or rather with this higher traffic that we are thinking, with 30% utilization, will there be a congestion in the city, or what has to be done in order to reduce the congestion in the city. So this is an example of a digital twin in, you can say, is now part of urban planning, transportation area. So very, very interesting. Okay. So when it comes to infrastructure, the major problem comes monitoring it while it's become, constructed. So having a digital twin model, this really helps you, and it saves a cost a lot. And then before you build, you see everything while it's getting built. You see part by part, so it's a really cost of. You can predict every part of the cost, and that's one of the major challenge of any kind of an infrastructure that's being set up. Processes is like same like power plant, and these are the areas where piping plays a huge role, different kinds of piping. So digital twin has got a huge implementation. Environment is coming up a lot because there are now mapping even the environment along with that. So the impact of an industry. So think of a compliance point of view, from policies point of view of a company. So be it a process power plant and everywhere, it's like, the environment is a concern. Now we can build an environment model across the plant and take necessary actions. Bulk material handling or material handling is, of course, another industry which is the digital twin has been being penetrated here. The challenge, the good part is here you can have a mostly electromechanical instruments and all machinery. So the dynamic simulation of these conveyors and belts, these are very, very important. The structural stiffness and this also. Utility is probably the second one after oil and gas, honestly, because this has got a huge impact. Is you can understand, this distribution system, the grids and all, if they are digitally twinned. Literally, we were doing a project where these grids, they are exposed to different kind of threats, be it vibration, be it sagging. There are more than 25 threats of this kind of structure. So with a digital twin model and the different sensors lying there, you can literally see, is there any issue or not? And you can really do a very well predictive maintenance for that. IIoT was there in manufacturing, so the digital twin has made it much more efficient. And of course, now you can have in every step, you can really do and see what's happening. Quality becomes much better, quality process. And of course, like it has got direct impact in ALM, like asset lifecycle management, quality control, everywhere. So manufacturing is probably the easiest industry where the digital twin can be implemented very, very quickly with a lot of IIoT and IoT devices and all. With this, I pause here for questions.
Excellent, Sanjay. This was a good introduction to what this particular forum is striving to do, the global emerging technology, and you touched upon the various emerging technologies, how it applies to the in the area of digital engineering. So thank you very much for the presentation. So folks, the floor is open. Please feel free to unmute yourself and ask questions, or you can put it on the chat as well. Either way, we are open. So let me ask some questions while others are thinking about it, right? So the examples you gave, Sajay, most of them are large industries, right? Um, do you see similar applications, let's say, in a much closer to the consumer? It is, let's say, for example, in the real estate, housing, not on the commercial side, but on the personal side, and how this can be applied.
See, real estate was probably the first industry, as I initially said, like the BIM was existing. And if you see the rest of the industries, we categorize BIM as a separate. The reason was the BIM has got a different, and it has a consumer facing. So before you buy a property, you can walk through. Before the property is built, you see the property. Before the property, or when the property is getting built, so you have got step by step. The property is making, you are putting up sensors while building the property, so that at least your maintenance becomes easy. Everything is, captured in the building information modeling. Nowadays, I think a couple of countries, they have got mandatory, policy rather from the government to have BIM in any building that you do, like the Burj Dubai in Dubai. So their whole BIM was done by a company based in Kolkata, I know. So they did it, so many years back. So the BIM and the real estate was quite matured, honestly. And the reason probably they were matured enough, I won't say that's of course a digital twin, of course, but that was because that was consumer facing, that came much earlier, honestly.
Another example which comes to my mind is tourism, travel and tourism.
Yeah, exactly. A lot of companies are doing now.
Right.
It gives you a complete virtual tour.
Exactly. Most of us, the way we have done tourism is we go to travel agent, you look at the travel book, you look at the nice glossy pictures.
Absolutely. Huge. Even undersea, forget about those, these are natural industries, which was out of my surprise. Like, I was just having a discussion with, this couple of guys from the naval area. So this undersea, I mean, I was amazed to see the progress that has happened so they have made a complete digital twin of the whole ocean kind of a thing. So there are some projects, you can see operation, they call this Nemo's Garden. Nemo's Garden is like a digital twin technology. I mean, this is basically to accelerate the underwater farming. Just imagine. Nemo's Garden is just to accelerate the underwater farming. So I mean, these are there is one organization called ILIAD, I forgot the exactly acronym. This is like an EU funded ILIAD, I think. So they are doing, for the whole ocean. So, and, mapping every part of the ocean so that another habitat can be built up and we can get maximum out of it. So that's a very interesting use cases.
Another use case I can think of, you can talk about is healthcare.
Oh, yes. I forgot to mention, but that's probably the most important, honestly. Yeah, I talked about engineering, so healthcare was not there as a use case. Right. Honestly, that is one of the beneficiaries and probably the most serious beneficiaries for mankind,
in fact, one of the emerging areas which I'm working on and pushing is this whole area of digital health engineering itself. It's a field which doesn't exist today, but it will be coming up very soon. So,
coming up, absolutely coming up.
Do you want to talk about a little bit? There's a question, but do you want to talk about tie-in this conference? It's focused on blockchain and other emerging technology. Do you want to weave in some of the applications through that into what you'll be talking about? Let's say blockchain as an example, or so.
No, can you come again?
I said, do you want to give some examples of blockchain applicability of blockchain into some of the examples you spoke about?
Yeah, because, the moment it is, big, for example, when you are thinking of implementing this kind of a solution for a city and all, like say in agriculture, agri-tech, correct? So you're making a digital twin land bank. So which is being used, what is the soil quality, everything, right? So now this kind of scenario, this is the best way to have this data secured is through blockchain. So of course, the blockchain will be one of the underlying technology for security, as well as having to handle this kind of huge data which is being shared. Of course,
Right. So we have a couple of questions coming up. The first one is it possible to apply digital twin in electricity distribution system or energy distribution in a city?
Yes, that is the utility sector, and that is the after oil and gas, that's probably the industry is going fastest. I give you an example. We did a project for the Ireland water distribution system. So there, the whole city has got this water as well as sewerage, both. So they had sensors and flow meters across the whole city and all. So you can literally see, we did the complete model, and then we are getting the sensor data in real time. So any anomaly or any prediction, we do a predictive model on top of that. So their whole distribution system for the utility is there. So do the same way, like, for the electricity distribution. In fact, electricity distribution system, the main use cases that we came across is the surge price, like, how you control the price surge, the through using digital twin as well as some predictive model along with that. What happens, like, you've got those distribution discoms, distribution companies, right? And you got the demand. Now, if you have this demand and beforehand, and then you can plan, then you can control the surge. So it's basically the surge prediction, honestly, or the demand prediction. If you do a proper demand prediction, the surge price will be controlled. So when you are buying this from the generation companies, the distribution company buy this from the generation companies, right? So you can negotiate a better price if you've got a predictive model in place.
So do you want to answer the last question? Yeah.
Yeah.
About your company, what kind of work it has done in this space?
Oh,
you may have touched upon, you want to repeat that again.
We have done a lot of things in the oil and gas, energy utility, in defense and transportation so far. These are the areas that we have implemented digital twin for last 2.5 and 3 years, more or less. Like in defense, we are doing very interesting thing, like, we are even targeting torpedoes in real time. So those are the very, and then the example of transportation that I gave, I don't know whether you were there, Johnny, that time, like for a city, you are doing the transportation modeling, like where you can have a urban planning as well as transportation traffic flow, both passenger and freight movement simulation. So that kind of. So we do World Bank. We work with a lot of financial. I mean, those kind of institutions, like even we did not do in healthcare, but we did something for during the COVID. We did some map of the city, like in 3-4 cities and the whole US for the fludemic. Like we mapped this flu and the pandemic. So that was not exactly an engineering digital twin cases. So that's why I didn't tell about that. But yeah. So that's also we did. So the data being our core expertise, and digital twin is the platform that we have.
So Sanjay, do you want to really touch upon the cost of implementing such thing? Because it's very clear that the cost is high, but then is it really high? I mean, so we want to just talk about that.
Yeah, when you see, if you break down the cost, so digital twin is not one technology, like it has got step by step, like the 5-6 steps that I mentioned. So every step has got some cost. Now, most of the companies, they have some step. Like if you go a matured company, they might have their already drawing. So you don't have to do a reverse engineering through drone, LiDAR and all, right? So they might have already some drawings available. So the cost of making the 3D model is simpler. Some companies, they already have 3D models. Then the cost is less. The next comes to different sensors and the data. Most of these companies, they already have SCADA or some kind of a process, system running already, but maybe additional sensors. And these days, sensor costs are not huge, like, it's not in billions. So, I mean, but again, it's not, I mean, that much costly, honestly, those part, the collection of the data. And the next part is the AR, VR, like the interaction, and those part are not also very, very costly. Honestly, for the augmented reality these days, printing the cost of the QR codes, putting it there and making an infrastructure within a local DMZ zone, so that even these companies, because of the security, you don't have to put everything in the cloud for responsiveness and all. So this has to be a kind of a within plant system, and that will talk to the cloud. So if you have this kind of an hybrid, cloud model, then your cost is not very high. Of course, that will depend upon the size, but more or less rough figure, I can say to build the entire model for a small oil and gas industry might be few $1 million, honestly. For a small power plant, it might be less than $1 million. So it depends actually, totally on the use case and all. I really, cannot have a number to say, but yeah, it varies a lot from few 100,000 to few millions.
So maybe your last question you've answered on the chat, which is the scale of the digital infrastructure needed to mimic the energy distribution system in digital twin.
Yeah, this is pretty complex, and not only that, it's pretty costly initially because it's all across, right? So the main cost for this will be scale up is possible, but the main cost of this will be collecting the data and making it fail safe, and then centralize and then put it in the cloud. So there might be, this we had tried in a small scale, but when you want to really scale it up for the energy distribution system across the country, this is a mammoth task, honestly. But with the challenge is like, those sensors are, you have to put it in the right, in that those, poles. So there the challenge comes, the physically putting those, making, doing a maintenance, of course, like, those things are the human cost, or, cost of maintenance is a pretty high. But otherwise, if you see, the basic technology cost is not much, honestly, because this technology is not very complex and not something new, honestly. We are just clubbing the technologies and putting it all together, stitching that. But the cost of the process and the operation we cannot help. That will remain. But it is possible to scale this up, honestly, with the latest cloud, hybrid cloud options that we have.
So I'll ask you last two set of questions, or one question with two different angles, something very different. But let's say I'm new to the industry, or I'm a new student. I'm excited by your talk. I want to learn about it. So what exactly do I need to learn? What do I need to do? Go get a degree, or how do I retrain myself to be part of this new area of?
Yeah, that is a very interesting question. Honestly, I don't have a right answer. The reason is, even if you see the companies, those who are in digital twin, either they are very big company, like GE, Siemens, and all those kind of companies, or there are boutique companies like us, but there are very few in numbers. The challenge, the reason why it is difficult, even to make it, so far as there is no degree or diploma I have seen in digital twin area, so at least in India, I don't know in other countries. Probably the reason is, if you see, the backbone is 3D modeling, those kind of things. So that's not basically a job of an IT, like it's basically IT enabled services or knowledge, whatever way you tell it. Then it comes a lot of hardware. Then it comes a lot of analytics. Then it comes of data science and data engineering. So it is not only one field that makes you a complete knowledgeable person on this as an individual. So probably a stream of engineering on diploma, if it is possible, that will really help to know each and every step. But in that, probably I do not have a right answer, but the bits of pieces of technology, IIoT, probably one of the stream the people should learn. Data engineering and data science. Data engineering is probably more important than data science at this initial part of their learning. And in the back end, a bit of GIS related technologies, and 3D modeling. And there are lots of open source are available now these days in the 3D modeling space, like Babylon, and lots of. So the libraries are enormous. So these are the three broad areas. So you make your model, push the data onto the model, predict, and generate some actionable insight. If very broadly, these 4 steps, if we can, emphasize, so they can learn accordingly in 4 different courses.
Maybe I can give us a little bit of an answer myself to the, how do you reskill yourself? You are an existing worker and you come to this space, and maybe IEEE as an organization which is dealing with all these various activities can be one of the possible ways to join and help learn some of the emerging areas. Anyway, this has been a very fascinating conversation, Sanjay. I love this. So let's give him a big hand, a virtual big hand out here.
Thank you.
Thank you very much for that question. But Sanjay, stay back, because we have another fascinating conversation with Jim. Jim, let's go through your presentation. Maybe we can have an impromptu panel between you and Sanjay.
Certainly, and appreciate the introduction. I also appreciate Sanjoy's background. I think was excellent. The presentation was outstanding, and I think it laid the groundwork for a lot of what we're gonna cover as well. So let me share my screen. Oh, excuse me just a minute while I get the slides teed up for you. There we go. Sanjoy covered a lot of excellent areas, and we're going to focus specifically on digital twins in healthcare, with a bit of a diversion into also focusing on unique aspects of security, which I think Sanjoy gave a great overview of some of the various technologies and ways to consider career paths for doing this. As part of that, I'd offer information security as being one we want to take a look at. I think we've had a great background so far on what a digital twin is, but just to kind of recap, and hopefully the graphic is useful. Digital twins really focus on digital emulations of any real-world physical system, encapsulated in a software object or model that mirrors all of the unique aspects of the process flow, as you can see from the diagram here. Data is aggregated from multiple digital twins, can be brought together into a composite view of multiple systems, which of course is important as we talk about here from a healthcare perspective. And I think we covered some of this too as well, but just to kind of offer how we got here from digital twins. Moore's law and computational scale. This is basically the increase in computing power in chipsets, coupled with the physical reduction in space that chipsets take up, and the amount of computing power available for any one given size chip. The growth of embedded devices and the use of IoT, the growth of analytics and AI and ML, and the evolution of those training models, and the evolution I would offer of user interface and user experience to AR and VR models as well, because AR and VR certainly plays an important role as far as a 3D modeling for digital twins are concerned. I believe Sanjoy touched upon some of this, but these are some of the major functional groupings associated with digital twins in various areas of process mining, data visualization, data science, and of course the collection and the process and storage and compute, of which we touched upon the importance of edge computing and IoT being major factors for digital twin systems and data collection for those digital twins. Just to show kind of an anatomy of a 3D digital twin model that breaks down some of those core components there between the supported services, the front end services where you can see the 3D engine being brought in, analytics and automation, the data engine, and of course security is mentioned there, and then of course your various source systems. And just to highlight, those source systems may be APIs to IoTs, they may be existing databases, they could even be just flat file structures of CSV or XLS, and then of course embedded devices and sensor technology that are gathering real-time data. Now, specific to healthcare, we tend to divide this up into three categorizations. You have process digital twins, such as models for large systems or facilities, like you see up there in the corner, which is built around Singapore General Hospital. I wanted to get my colleague from Singapore, who has a startup focused on Singapore General Hospital and modeling process flows within the hospital, but unfortunately he wasn't able to join us for tonight. System digital twins, and as you can see, that refers specifically to things like our heart, other major bodily systems or organs. Dassault Systems has put in about 10 years of advanced research and analysis for what they call the Living Heart Project. Their 3D digital twin model of the heart is good enough that they actually use, they have researchers who participate in running experiments and clinical trials using the using the digital twin of the heart as an alternative to actually using a physical heart for medical research. And then lastly, the most sought after and probably most sophisticated digital twin model would be a digital twin of a patient, which would be that system of systems process model combined into some sort of composite view for all of your organs, your systems, various biome factors, exome factors, etc., which can be used for research and for care delivery. There are some unique considerations around digital twins in healthcare, especially because they're modeling particularly critical processes. Not to say that in an energy grid or water distribution it isn't critical, but if you're ultimately going to use a digital twin around clinical care and clinical diagnoses, you know that you're applying life safety type issues and patient safety in using those digital twin models. There's also unique regulatory requirements associated with the data and privacy and ethics, especially the ethics around the AI and the ML models that are being used for the purposes of your digital twin and your analysis. I've been actively involved with the Digital Twin Consortium, and recently we've come up with a framework of trustworthiness that's starting to focus on what are considerations for secure software and digital and data for digital twins, considerations of IoT and device integrity, considering zero trust principles, and we'll spend a couple of slides about that. The use of decentralized identity with both the IoT devices as well as the digital twins themselves. And then with that, the concept of trust profiles. How do you build a trust framework around components of digital twins, and how those digital twins interact with other digital twins, to be able to ensure that only proper data is being shared, that you're using minimum necessary data sets, etc. And again, remembering you're using oftentimes protected health information or sensitive health information for consideration as part of that digital twin model. So you want to make sure that you're enforcing trust models between those digital twins in use, and that there is integrity and trusted frameworks. So this leads us to the concept of identity and zero trust in digital twins. So as IoT and digital twins, have increased computing power, emulation, and real-world response and take on more characteristics of a physical system or an individual, you have to start considering what type of unique identity characteristics do we associate with that digital twin or the components of that digital twin for the sake of data integrity, and using these modern principles called zero trust architecture, as well as identity principles such as selective disclosure and zero knowledge proofs, which we used in decentralized identity. So zero trust identity assumptions is that every trusted user is authenticated as part of a zero trust model. I don't trust you, you don't trust me. So we establish a trust framework to be able to agree to the terms by which we connect, share information, and participate as part of a network. Technologies such as identity credential and access management, which have been traditionally used for identity. These include things like two-factor authentication, continuous monitoring, etc., and then other identity management and authentication tools. But as we'll touch upon, the environment for digital twins and IoT is a bit unique. And so traditional IAM and ICAM type solutions aren't always as applicable, and nor are they as efficient when you're trying to enforce that sort of dynamic security in a digital twin environment. So just to reinforce, what are we talking about when we're saying identity? And these are defined, as you can see in this NIST special publication on zero trust architecture. It refers to the information on an entity being used by a computer system that represents an external client. And most importantly, that client may be a person, it may be a system or service, or it could be an individual device. In DoD guidance on zero trust architecture, they specifically refer to person entities and non-person entities to recognize the fact that it may be a physical device or an IoT device that has to have those identity and characteristics considered as part of the network. So for zero trust, client identity includes the user accounts and associated attributes assigned to the enterprise to authenticate those automated tasks. And you can see more of this if you read the NIST special publication 800-207, Zero Trust Architecture, which you can find at nist.gov. So why is identity important when you're looking at a zero trust architecture model? Well, it assumes no implicit trust. Again, I don't trust you and you don't trust me. So we have to continuously analyze and evaluate what are the risks in our communications and the assets sharing information, the business functions, and making sure protections are in place to mitigate that risk. That oftentimes minimizes things like access to resources, or make sure that subjects and assets are continuously identified for needing access, and then continually authenticating and authorizing that identity relative to what the request is. There may be a case where an IoT device asks for some certain information as part of what it's trying to fulfill that in one case is acceptable, but if it asks that information again at a different time, it's not acceptable for various security and risk mitigation reasons. So I mentioned there's some challenges around what we've traditionally done with PKI structures and the like for identity and access management. And they're particularly difficult in IoT and smart devices and digital twin models. As you can note there, the managing of the device and user identities and the relationships faces a lot of architectural challenges, mainly because traditional authentication mechanisms just weren't designed for the sort of dynamic edge networking, IoT type networks. Also, there are challenges with the way IoT manufacturers establish their proprietary approach to naming and identifying these devices, and that makes it very difficult to understand the inventories, the directories, and apply the sort of PKI architecture that we've historically used for identity. Next, IoT systems need to go through a series of stages during their life cycle, and as they go through those various life cycle stages, the way their identity is managed and assigning characteristics for access management can be complicated. And then lastly, there's just not a good common operating framework and security framework for device manufacturers to adopt and for consumers to be aware of. So going forward, some of the things we have to look at are what we would consider a next generation identity management solution specifically for digital twins and IoT encompasses a couple points. First of all, privacy preserving. Privacy preserving means that aspects of the identity and the sensitive data are controlled at the identity level. And again, that identity may be associated with an entity, a non-person entity like a device, or it may be associated with a person that's controlling the network. In each case, you want the individual or the device to be able to control how information about themselves and what they're doing on the network is limited in their disclosure until such time as it's proven that they're part of a trust framework that can be leveraged for the information exchange. And one of those techniques we use is called zero knowledge proofs, which is a cryptographic method, which we'll touch upon another slide, to basically say, you don't know who I am and I'm not telling you yet, but I can present something cryptographically provable that establishes we are part of the same trust framework. And once you establish that trust framework, you can go on to selectively disclose other additional information about yourself or information that you have to share. There's layered authentication mechanisms. These use different approaches to cryptographic and application-specific authentication. It may be two devices have to prove to each other they possess certain public keys, and in doing so, then be able to share private keys as part of the trusted requirements of the network and how the data is being handled at the application layer. And of course, most importantly, you want all this to be standardized with an open approach, which you remember I mentioned right now is oftentimes proprietary to the device manufacturer. So we have things like decentralized identifiers, verifiable credentials, and these are all based on open W3C specifications, which I'll show again in another slide, that can be used by researchers to build these solutions on well-tested data models. And one last thing is being able to leverage JavaScript object notation and JSON for the basis of your encoding of both the credentials, the documents, and the information that's enclosed on the IoT devices. As we've gotten into more processing power at the IoT device level, things like JSON objects are something that are much more capable of being processed than, say, older systems or the type of PLC controllers you have in a SCADA system, et cetera. Also of importance for healthcare structures rely on HL7 FHIR messages, and HL7 is based on JSON as well. So you can immediately see a code development model that refers to healthcare data as well as those digital twins. I mentioned before about decentralized identity and verifiable credentials. As you can see, they're based on the World Wide Web Consortium W3C standards. They're JSON objects. And on the left here, you see a modeling around the layers of information that are enclosed in the verifiable credential, the metadata, the verifiable claims, and then the cryptographic proof that supports to be able to exchange, store, and retrieve those credentials for verification as part of a zero trust type model. And this is what we call the verifiable credential trust triangle. You remember I mentioned before about trust frameworks, and in this particular framework, you have some issuer that's digitally signing and issuing an attestation to the holder that says this person is, or this device is who they say they are, but then that holder is able to choose how they present their credentials to the verifier or the verifying device. And there is a verifiable data registry, generally in a decentralized blockchain system, that allows that system to be enabled, maintain privacy preservation with the holder, selectively disclose what they want for information, and enforce those rules around zero trust. It just so happens that a lot of this is embodied in the Linux Foundation Trust Over IP Foundation. We've developed an entire technology stack that addresses each of these layers that provides standards and specifications that tie in those verifiable credential principles and the use of decentralized identifiers, which then can reinforce this sort of zero trust architecture view that you want for your digital twins and associated IoT devices. And then just to kind of put it together in a slide that shows kind of the technical approach, you can see here, this translates that trust triangle framework into a process flow that shows you where each of the components reside and how the different methods of authentication and cryptographic exchange take place. Yo, thank you very much for the opportunity to present, and happy to hang around and answer some more questions.
All right. Thank you very much, Jim. That was excellent. It was a great compliment to what Sanjay presented before. The floor is open again, folks. You got a very overarching perspective from Sanjay, and then a very targeted, focused perspective from Jim. So perfect compliment to each other. Let's see if there's some questions there. Besides it being a great presentation, I agree with that, Tito. So I'll wait for audience to ask some questions to Jim. So while audience is asking questions, Jim, feel free to ask. Maybe we can do an impromptu discussion between you and Sanjay. So Sanjay, chime in and let's have a conversation here while our audience is getting warmed up as well.
It was very interesting, Jim. In fact, I mean, while your area was in the identity, like privacy preservation and all, so there was this is from an authentication perspective, and we did a very interesting thing on that, on the differential privacy part of it. Like once the data is shared, how can you protect that? Can that be reverse engineered? For example, if you remember, a couple of years back, the US Senator's health record was hacked, not just by reverse engineering, just by having some peripheral data. So mathematically, it has been proven, like, when you are sharing the data, it can be, identification can be possible by giving some complementary data sets, which is external systems data. Now that problem was kind of, now being solved in using differential privacy, a very similar approach on what you explained. The only difference is instead of doing some hash here, which was our de-identification algorithms most of the time for the data, but what we are using a noise in the data, so that the way the noise is being put, your aggregation level information remains intact, but the identities goes wrong. I give you an example, like, if there is name, age, and gender, very simple. We used to have this age in a group earlier, and of course, never used to change name, the gender, but we used to change the name and all. But now even you can change gender. Still, when you are doing query on your data set that's being shared, the group by queries will be intact. So your distribution will be intact. Very interesting. So that's how, this differential privacy thing, I think that will be complement to your authentication. So that will be more of an authorization and the data sharing, how you protect the reverse engineering of the data being shared.
Yeah, I think that's an interesting approach. Yeah.
So I'll ask a question to both of you. Feel free to approach it from your respective perspective. We all live in the world of mobile technology today, where we access information, we disseminate information, we interact, we play everything through our mobile device. So in terms of digital twin and the interface, is it sufficient in terms of horsepower? Is it sufficient in terms of landscape, the view to achieve some of the things we have been talking about, or we really need a larger display and things of those nature?
When I was at the Open 3D conference a couple of weeks ago, and we were talking about Open 3D engines and digital twins, the general trend was expectations that your augmented reality capability, headsets, not headsets at BVR, but glasses and enhanced screens would probably kind of fill the gap, because you're right, you can't necessarily get everything you need for a digital twin right here on this phone surface, but bringing that into, say, an enhanced display within your glasses or something that projects from your phone for an augmented reality would probably be much more beneficial, or much more visually stimulating.
Sanjay, any examples?
Yeah, I think you are right. The more we are decentralizing the computational power, so we are basically putting it in the central part. In the mobile, we are keeping it very light. And nowadays, if you see, the similar approach has been the gaming technology. So you can literally play any game on earth in mobile. So, and those were huge CPU and GPU intensive earlier. So if we can solve that one, those kind of things, this is much less CPU consuming, honestly.
One of the areas both of you didn't touch upon, but again, it's part of our ecosystem is the whole robotics and its introduction in the human interaction in these various areas. And the interplay which will now take place between the human and the robots, whether it's the manufacturing sector, supply chain, or anywhere else where. So would you want to talk about the digital twinning of those itself as well into the environment?
Yeah,
Yeah,
you could
that,
almost look at, go ahead, Sanjay.
no, please carry on.
I was just going to add that I think you could look at, say, the digital twins for each of those robotic processes, and find ways to be able to leverage the digital twin for optimization, identifying of issues before they occur, as well as be able to augment and improve the programming for the robotic technologies, depending on what they were being required to do within the system.
All right, Sanjay, you want to answer the question before?
Just to, definitely, and we can go more cobots, when we have this integration possible, like collaborative robots. So now that's where the digital twin comes a huge benefit. Effective. Right. I think somebody has got
I have a hand up, so please go ahead and can you go ahead and unmute, or do I need to unmute you? Let me see. I think you should be able to unmute and ask.
Yeah, I think, one of the challenges that we see in digital twin, you mentioned now cobots, like as long as all these companies are not using standards, some kind of ID step, whatever models, or some kind of kinematics embedded into all of them to put all different manufacturers, like we cannot really use true digital twin in many places because they don't want to speak the same language, basically, in all these devices or whatever we need for these exchange to happen. And also, I think, like when you were talking about healthcare, you know what I was thinking? I was thinking, what in future they become like Apple and charge you for every single download, for every single thing. So, they lock your digital twin about your information when you need help unless you pay. That's really scary.
So I'll answer that a little bit here. So some of the regulation clarification which are coming in is exactly to stop doing that. It was always there that the records were owned by the patients, but that was not really enforced. Whereas now, at least in the US, we are seeing some of the enforcement are coming in where you cannot be charging for your own health, access of your own health information. All right. Anybody else has any other questions? Jim has some internet issues, but we need Jim's digital twin here. We are missing that.
If my digital twin has better internet than I do. Yeah, I think Luis brought up a good question though, because I think you can inadvertently create proprietary paths where, let's imagine a near future where, hey, all of your data is available in your record, and we all know that your records have lousy data in them anyways. But if you want to have a digital twin where all of that is optimized with, updated algorithms and the like, that costs extra, or it's proprietary and you can only get to it. So it's compliance with the law, but it's not optimizing a potential, digital health technology.
And it's scary how much breach can happen. I'm one of the people who, when they have Anthem breach, my identity was compromised. I have to pay now monthly fee to make sure I capture if anybody, steal my social. And that happened because of the Anthem.
Yeah, my data was stolen in 2015 with the Office of Personnel Management, and then stolen again in 2014 with Equifax. So,
No.
My God. All right, so that was good comment there. Anybody else has any thoughts and comments? before we bid goodbye to our two experts here?
Well, it's
Right.
been a pleasure. Thank you for the opportunity.
Yeah, absolutely. So thank you, Jim Sinclair and Sanjay Chatterjee, for that excellent presentation and conversation, and to the audience for keeping us engaged. Thank you very much. We end the session today.
Thank you, Gora. Thank you, everybody. Bye-bye.